The world is watching. Come on. There we go. I hope you guys can hear that on YouTube Live. Hi, everyone. Welcome. I'm Sasha Zelenovic, and I'm a technical marketing manager at Red Hat. I do a decent amount of things, but one of my favorite things to do is organizing these vLLM meetups. We've probably done about 40 in the last less than a year. Year minus 8 days was our first one in Boston. And it's been a packed house pretty much everywhere, and it's clearly like this in Vienna too, so really excited about that. We tried to organize actually something in Vienna for a while now, and we struggled a little bit, so I want to just shout out Christian, Basti, I don't know where you guys are, I see Christian, Eldar, thank you so much for really pushing me to come here and involving the community and really organizing this. I really appreciate that. So, as I mentioned, I work for Red Hat. At Red Hat, we love, obviously, vLLM. We're the leading contributor to the vLLM that's better. We're the leading contributor to the vLLM project. About 25% of all the contributions that come into vLLM are from the Red Hat team. We have more than 10 core commuters on staff. I keep hearing 12, but it changes all the time. Michael, how many core commuters do we have on staff? 13, so it's growing every time. I'm actually struggling to keep up myself. We also build and maintain adjacent open source projects like LLM compressor for taking massive large language models and optimizing them without losing any accuracy so they can be faster and efficient. You'll hear about LLM compressor shortly. Guide LLM for benchmarking real world inference. Speculators, LLMD, you'll hear about most of these things, if not all, in just a few minutes. So really Red Hat is open AI, really end-to-end. So open models, open inference, and then flexibility of hardware, so hardware of your choice. And then community, so Red Hat is just one piece, but vLLM is way bigger than just one company. 70 organizations contribute to the project actively, many more have before. Over 2,000 contributors, right, Michael? Yeah. To the project? Yeah, that's your stat, I don't want to misrepresent it. And that's what really makes the project so amazing. There's so much involvement from the community and from all of you. We're driving more than 1 million installs of vLLM each week, 1.9 million last week. I'm hoping that keeps up, but it's definitely a big jump. vLLM runs on over 500,000 GPUs at any given moment. And that's really, to all of us in this room and to all of you. So really thank you for supporting the project. I do want to shout out our sponsors. NTS Data, thank you so much for the beautiful venue. You'll hear from Christian in a minute or so. Really appreciate the venue. Canva, wherever you guys are, thank you. I'm really excited about your session at the end. We'll talk about it in a second. NVIDIA, thank you for supporting. Thank you for running the workshop. And of course, Red Hat. So we're really happy to bring you this. All of these companies are very active in the vLLM project, and you'll hear about a lot of the work we're doing just shortly. So let's just do a quick audience warm-up. I see there's plenty of energy. With a raise of hands, how many people took public transport here? Huh, very European. That's very, very different in the States. How many people drove a car? We're not going to shame you. Huh? Some shame, I guess. How many people flew here? All right. Where did you fly from? Oh, wow, okay, so I think you might have me beat. Ours was only 7 hours, you're probably a little bit longer, so pretty cool to see, obviously a lot of Vienna, but nice to see people from around the place coming. And then let's get a little bit more serious. So who here has used vLLM before? Okay, pretty cool. And then who's never used it? All right, it's gonna be a learning experience for you for sure, awesome. Who is actually running vLLM in production? Awesome. So speakers, take a note. There is definitely a diverse audience here in terms of knowledge. So any chance you have as you talk, the slides are going to be very technical. So for speakers, any chance you have to show the benefits, explain why this actually matters, how the approach is different, please take a chance to do that. And let's quickly go into the agenda. So we'll start with, I'll pass it to Christian to say a few words, and then after that, we'll give it to Michael Goin. Michael is a core committer on the vLLM project. He's been since pretty much day one. He'll do an intro to vLLM and share the project update, so we'll get technical pretty fast. We'll pass it over to Dan Alistar for transforming LLM quantization, so that's the model compression piece. We'll talk about the speculative decoding, and then we did change one session. We were supposed to do distributed serving. You'll see plenty of that through the slides, but what we'll do instead is what we'll do instead is we'll bring the speakers here and we can have a Q&A. We would love for you to be involved in the Q&A. Whoever asks a question, I have something for you. It's nothing big, don't get too excited, but we do have something for you. We'll take a quick break, if time permits, hopefully, and then we'll come back to talk about communications and MOE architectures. And then the one that I'm really excited for, the last session, is from Canva, really talking about vLLM in production and how to serve vLLM to 260 million users. I love that stat. Okay, after the talks, there'll be a quick 3-question survey. Would really appreciate if you can just keep thinking or just keep in mind what's good, what's bad about this meetup. As I said, we're doing so many of these, so anything you can share would be very beneficial. So there'll be a QR code for that. We're streaming this, we're recording this, we'll send you the recording, we'll send you the slides. And with that, again, welcome, and I'm gonna pass it over to Christian for a quick intro.
Thank you, Sasha. Yeah, don't worry, I don't have a lot of slides. I'm just representing NTS. So my name is Christian Schuster. I'm sales expert for data center and platform technologies at NTS. NTS is a full stack system integrator. So we're doing infrastructure, platforms, AI out of the box. And our motto is relax, we care, as you can read all around here. So we are thinking out of the box and try to assist the customers and of course you all guys here as early as possible and assist you with any questions. So we're pretty happy to have all of you here. We see the AI community in Austria is pretty strong. You know, Peter Steinberger is one of our Austria fellows. So nice guys all around here, and happy to have you all here. Thanks to Canva, Red Hat, and NVIDIA to be here. And yeah, we're looking forward to a nice evening. Have fun, and if you need anything, just let us know. And yeah, I'm handing over to Michael now. Have a nice day, have a nice evening, and catch you up soon. Bye.
Oh yeah. Sorry, thanks. Hi everyone, my name is Michael Goen. I've been working, are the slides gonna go back? Yeah, thank you. I've been working on vLLM for over 2 years now. My background is in HPC and performance things. So of course we love working on LLM inference these days. I'm a principal engineer at Red Hat and a core committer on the vLLM project. You may know me as M. Goen on GitHub. Yeah, I'm going to cover a brief introduction to vLLM. Hopefully you can get inspired by some things and look into more concepts that are interesting. And we're going to cover a project update on what we care about and are focused on in this quarter and onwards to the year. So I'm going to cover a lot and ask questions at the end. So first, if you aren't familiar with vLLM's goal, it's to build the fastest, easiest to use open source LLM inference and serving engine. Also, the most popular and widely used one as a result. And you can see from our quick start guide, we like to keep it as simple as possible if we can, making just pip install vLLM and hopefully start running your models right away on your very expensive GPUs that you want to utilize. So what is vLLM and why is it popular? It's grown into a huge project and community on GitHub. It has over 70,000 GitHub stars, hundreds of PRs submitted every month. It's deployed on millions of GPU hours every week, both on community and hobbyists, and also at enterprise production scale. We have over 10,000 active members on our developer Slack, which you're very much welcome to. And the project itself has over 2,000 contributors, unique people that have landed code in the project, which is really crazy for a project that's only been around since the middle of 2023. As I mentioned, pip install vLLM, vLLM serve DeepSeek. We like to keep things simple and as fast as possible on whatever hardware you have. The reason why vLLM is so popular is part of this ease of use, also because it supports hundreds of different model architectures, especially the state-of-the-art ones, as they release on day 0. It supports, not only great performance on NVIDIA GPUs, but also a variety of other hardware accelerators through the software interface that it defines. And it can run those models very efficiently across more than one hardware accelerator with many different types of device parallelism, which I'll briefly cover later. And of course, vLLM itself is an inference engine and a specific project, but it's part of a larger ecosystem with many sister projects and forks, which we have, like vLLM Omni, which we'll briefly cover, LLM Compressor, LLMD, many that Sasha has already mentioned before. And to just drive home like how important vLLM is in this open source AI movement, is it was voted by GitHub as the top open source project by committers or contributors last year. Pretty crazy seeing it above like VS Code, but it definitely drives home why it feels like so much work to maintain a very active project like this. Next, I want to say, definitely the large success of vLLM owes a ton to PyTorch at its core, giving us the abstractions below us to extract over a variety of operations and hardware, and ultimately, build greater abstractions on top of that. And we very much value our close collaboration with the PyTorch team on many different aspects and co-developments that we do there. So, just to reiterate, vLLM's purpose is to essentially broadcast all the hardware optimizations that we're getting from this, very expensive, advanced new hardware to all of the past and future models that people care about serving at scale. And we want to make that abstraction as clean and simple and idiomatic as possible, so that people can build on top of it. And of course, many applications in the ecosystem builds on top of vLLM, as it's just hosting the model. You need to figure out how to make the models do useful things, and our job is to just host that efficiently. So that's the quick introduction to vLLM. Next, we're going to cover what we care about in vLLM right now and the main areas that we're making progress and focused on. And all 5 of these categories correspond to channels that we have in the vLLM Slack and special interest groups where we host weekly meetings where you're invited to participate and give us feedback and keep up with what we're doing on a weekly basis. So first, we'll go into the core. Can I use this? No. So if you've been following around with vLLM, you're probably familiar with the v0, v1 change. This isn't a version for vLLM, but rather a rewrite of the engine core, keeping the front end and the back end the same. But ultimately, it's a refactor we felt we had to do for vLLM as it grew from its original research project, the page attention paper. But of course, there's many other optimizations that have arrived beyond page attention in efficient inferencing. And when you do the cross product of feature support, it was quite bad in v0 because we sort of had to hack and tack things on one after another. And so we wanted to take a step back and redevelop the core into vLLM v1 so we can have much better cross products and addition of making sure speculative decoding works with prefix caching and with structured outputs and FP8 KV cache and so on and so forth. And we're really, and hopefully you haven't really noticed this. We've tried to maintain a lot of features the same way. And as of 0.11 on vLLM, there is no more v0. Everything you're doing is on v1. Another place where we've invested, early on is the hybrid KV cache manager. When LLMs started, mostly all the layers were, full global self-attention, but especially as we scale models to longer and longer context lengths and larger and larger models, we, find that we can, use much more hybrid forms of attention using linear attention or sliding window, ways of decreasing the cost of attention, and very importantly, the size of your KV cache. To make the model inference more efficient. And you see this with recent models like GPT-OSS, Nematron Super, which just came out, Qwen 3.5, and Qwen 3 Next. But ultimately, this is like a really hard design problem inside of vLLM to manage and keep up the features that we have, like speculative decoding and prefix caching, and make these work with these leading state-of-the-art research methods like Mamba with state space models with sort of a recurrent state or gated delta networks and so on. But ultimately, this abstraction allows us to deal with heterogeneous KV cache between each layer and abstract that away for the other things we want to build on top of managing or moving that KV cache, which we'll cover a bit later. Next, there's async scheduling. Traditionally, vLLM had a synchronous scheduler, meaning that the CPU would schedule and figure out and prepare the input for what batch of requests need to execute on the GPU for the forward pass. And then that pass would execute, and then we'd do the same thing again. Asynchronous scheduling just breaks that dependency and means that the GPU can execute step n, and the CPU prepares step n plus 1. So obviously, this is really important as the GPUs keep getting faster and faster, and people want to drive interactivity higher and higher. And this has been on by default since 0.14. We're on 0.17 now. And we're enabling more and more features to be compatible with this. And this gives a really big throughput improvement, especially for small models. And as these very large models that are MOEs have very high amounts of sparsity, so you can have a lot of requests, but each of those requests are only activating a few billions of parameters of weights at a time. So that CPU bottleneck becomes really, really important, and this is key to avoid that. Now, of course, we don't want to stop with V1 and just asynchronous scheduling. We want to take a step back at the even larger group of features that we've implemented by now and look at the future and see how we can refactor things from there. So we've started work on Model Runner V2. This is a bit of a smaller refactor, more focused on the Model Runner specifically. But the Model Runner has grown into essentially one Python file that's maybe 7,000 lines of code, and we would like to modularize, break that up, and make it a lot easier to add new features without affecting other features so much. So there's many reasons and plans for work that we have here, but I'll just cover a few briefly. One of the key things is we introduced the persistent batch idea in V1, where we manage a contiguous block table of requests on both the CPU and the GPU. However, this means as new requests finish and end, we need to reshuffle these requests around because we require them to be contiguous rows of requests. And this causes a lot of complexity in managing this block table state. In Model Runner V2, we want to decouple this from the CPU representation and the GPU representation, where we want to manage a static block table that's allocated ahead of time and doesn't need to be contiguous. And then we use that information in order to construct our actual input block table on the device each time. And this also allows us to take advantage of other more modern features on modern GPUs like Grace Blackwell with universal memory addressing. So we expect to see performance improvements from there as well. And then also, we talked about asynchronous scheduling. By now, it's clear that this is like an absolutely necessary thing, and it needs to be a first-class citizen. So I mentioned how we got this working in V1, but it still ultimately relies on a barrier where we decide when the state that we've prepared is ready to move from the CPU to the GPU, and we need to explicitly check that barrier. In V2, we hope to eliminate that race condition entirely by just adding a temp state and copying the self.states that stays on the CPU and making it very explicit what states we are moving to the GPU rather than having it be an implicit assumption by just what's in self.states. This sounds really simple, but I promise it's a really important distinction. So that's all I'll cover there. We have a lot to cover. Next is speed of light or model performance or model bash, as we like to call it. So first, when we talk about performance, we need to talk about accuracy. Accuracy is obviously extremely important. Many people use vLLM as the reference implementation for model releases or reference model behavior. So it's really, really important that we maintain vLLM to have good accuracy by default and make it easy for users to opt in to maybe things that trade off a bit of accuracy. And we also work very heavily on features that are useful for training in RL, which I'll cover a bit later, like batch invariance, to improve the determinism of running your models. So as they run at different batch sizes or different scales or at different times of day, they can hopefully give the same answer at the cost of a little bit of performance when the accuracy and determinism needs to be kept 100% the same all the time. So accuracy is really important as well. But onto performance and how we guarantee these things. We invest very heavily in our CI, both in vLLM and in the PyTorch project partnered with it, to continuously benchmark vLLM on a per commit and nightly basis, to look for any regressions and of course improvements that we see in the project. So as dozens of PRs are merged every day, we aren't making backward steps. And we spend a lot of money on CI. We spend basically $1,000 a month, or $100,000 a month on CI, thanks to our generous benefactors, in order to not only test but also ensure the performance, as so many people are relying on the project in production. I mentioned we work very closely with the PyTorch team. Torch compile is a key part of that in vLLM that we've adopted very heavily. We use it for automatic kernel generation and for keeping the model definition very simple and clear PyTorch eager based. So it's easy to add new model definitions into vLLM and allow us to write optimizations and fusion passes that are generalized between model definitions, as Torch compile allows us to get a graph representation of all the operations and fuse operations together that are general patterns. In vLLM, we are continuously working on improving performance. In this example, just within 1 month, we worked very closely with NVIDIA on pushing the performance Pareto frontier of GPT-OSS on Blackwell GPUs, adding new customized MOE kernel backends, optimizing existing FP8 attention backends, and as I mentioned before, introducing new graph fusions to fuse operations together that particularly affect latency on models like GPT-OSS. And this is like a key example of just the continuous improvement. And another one I can show is on DeepSeek R1, MVFP4 on Blackwell. On the left, you can see these are all different CLI arguments you can enable, and the improvements, the performance improvement can increase by 60% just by enabling different arguments and enabling new backends or optimized kernels. But this isn't enough. We don't want these things to be opt-in. We want to choose the best performance by default for you as we get these better features. So here's a benchmark I actually ran the other day on just vLLM 0.14 versus vLLM 0.17, offering basically 1.5x to 2x improvement on this DeepSeek model with just this simple vLLM serve command, keeping the command and default performance, keeping the command the same and improving default performance over time, making your hardware much more valuable, which I think we all hope is the point of software. Next, we focus a lot on speculative decoding, which Elder will cover a bit later. And within vLLM, we're working very closely with model labs and companies that are pushing the Pareto frontier of efficient speculative decoding methods. Recently, we've been investing in parallel drafting methods like PARD and Parallel Eagle, and most recently dflash, where we're able to keep the performance of speculative decoding at a very high level while predicting more than just 1 or 2 tokens at a time, predicting 7 tokens at a time, 14 tokens at a time, while not being bound by the overhead of running the draft model repeatedly to validate through the target model. As I said, Elder will do a much better job explaining speculative decoding. We don't have that much time. But to sort of close that loop, we have the speculators project within vLLM, where we're not only enabling these methods and these trained models to run in vLLM, we're also building the infrastructure to train these speculators yourself so that you can better train these models to align with your specific workloads, your specific fine-tuned models. And speculators uses vLLM in order to generate data to train the model to be well aligned with running the model in vLLM. Next, we have distributed inference or large-scale serving, which is obviously a very key workload. I've already mentioned vLLM has many different types of parallelism. Back in the day, we started with pretty simple tensor parallelism or pipeline parallelism, splitting up the model at each weight or across layers. But these days, we have a lot more types of parallelism, especially as we have large mixture of expert models and disaggregating prefill and decode operations within these large production scale deployments. And so we've been spending a lot of time on disaggregated PD. The reason why this is so important is that it decouples the two very different scale operations in vLLM, which is prefill and decode. Prefilling is ultimately processing your input context. It's more of like a compute-bound operation. You're running large batches of tokens in order to serve you a very fast time to first token. And decode is when we're running one token at a time for the response of your model. And this is much more likely to be running at a small batch size and be much more memory bound by the very large billions of parameters of weights we have to read for each token that we're getting out. And so if we separate these operations instead of co-locating them in an aggregated vLLM instance by default, we can meet the latency separately for both the input token, time to first token, as I mentioned, and time per output token for your decode, and ultimately also choose different things like different types of parallelism depending on how we want to scale these operations. And here's actually a real graph shared by Mistral at the Zurich vLLM meetup last year of a production deployment they have for Mistral Medium and showing the P99 inter-token latency. Obviously, they have a tight threshold here for a standard aggregated deployment and a disaggregated deployment on the same number of GPUs, where because they're separating the prefiller from the decode nodes, we're able to keep the decode nodes very stable at an order of magnitude better P99 latency, and thus meeting the latency SLO that their clients probably appreciate very much. We achieve disaggregating prefill and decode through a general interface that we defined in vLLM and has been adopted by the community called a KV connector. This is just a general idea, or at its most basic level, you have a vLLM instance that has a KV connector in its scheduler. You have other vLLM instances that have the same, and we have some sort of data transfer layer, which can either be like RDMA, or from device to device, or can be through TCP, or can be saving to storage and retrieving from storage. And we integrate with like Nixel, LM Cache, Mooncake, and as I mentioned, we have a sort of plugin interface for KV connectors, so you can build your own KV connector plugins and even use them for more exotic things like hidden state extraction, like we're using for training speculators in speculators. Next, the really big thing we focus on for distributed inference is wide expert parallelism. This is a key optimization for running decode for large mixture of expert models like DeepSeek or Kimi K2 that are now trillion parameter models. We want to run these models at very large batch sizes across multiple nodes of GPUs. So in this case, we're running on, imagine like 32 H200s, one model split up with different experts across each device, and data parallel replicated attention across each device. I think Dan will hopefully cover a bit more later on the different types of communication we need and why this can be a trade-off that's worth making. I can't cover too much here. But we are able to show the performance benefits of this and ultimately replicate numbers that leading labs like DeepSeek have shown at scale, where this was actually quite a few months ago. We've built on this, but we're able to serve DeepSeek R1 at 7K tokens per second per GPU and 2,000 tokens per second per GPU on decode, running at 96, running across 96 H200 GPUs for a single model, serving thousands, if not tens of thousands, of concurrent requests, and ultimately trying to make the most money out of the GPU clusters that we have available. This takes a lot of kernel optimizations and system optimizations in order to deal with things like expert parallel load balancing, implementing dual batch overlap to hide the communication, the extra communication required by these all-to-alls between all 96 of these GPUs, and of course, optimizing things all down the stack, which which is great to see in the community that we have. And we've of course expanded this to more modern GPUs like GB200, where we're able to show a 4 to 5x improvement in the same deployment, or rather per GPU for DeepSeek R1, just by upgrading the hardware, and able to serve over 10,000 tokens per second per decode per GPU on the decode nodes, which again is a lot of work in optimizations, and we're still working on even more, and have expanded to Grace Black GB300, and yeah, there's a lot more in store here. Next, there's multimodal, a really key part of vLLM, and especially the open source community as we get more capable models coming out all the time with multimodal inference. One thing we've introduced recently is, of course, we've talked about prefill decode disaggregation, but we also can disaggregate the encoder that we use for image or image, video, or audio processing. As these pre-processing operations can often be very, very compute heavy, and again kind of disrupt either the prefill or decode we're doing on the autoregressive language model backbone. And actually in this blog, we show the benefit of disaggregating the encoder on various scales of vision language model deployments. Next, as I've mentioned to some people earlier, we're still evolving the core things in vLLM, like the scheduler, to support new model types that are coming out, such as models that support real-time streaming inputs, like Voxtrol and Qwen3 ASR. So as we're producing, these are both speech to text models that, as you are translating or transcribing the speech to text, we're also adding in new speech, like when you're recording live and want a live conversation. And so this means we need to change the scheduler in vLLM so it can support, as requests are running and producing tokens, they can also take in new tokens, and they'll schedule kind of prefills and things. And so we're really happy to do this co-development with the open source model labs, and ultimately bring these standards to open source and to you, so they're not just implemented by the closed source APIs. And next, sort of the future of where we're looking for where model architectures are going as a whole. We've started the vLLM Omni sub-project, which builds on top of vLLM and ultimately makes pipelines around the core of vLLM to support arbitrary multimodality encoders and arbitrary multimodality decoders, especially as some models start to use diffusion transformers, or variational autocoders and various other methods. And this project is quickly growing at a very fast rate, and really important as we are supporting and seeing more of these omnimodality and multimodal models coming out in the community. So please give it a try and join in if you want to start early. And lastly, I want to cover RL, reinforcement learning. This has been a really important use for vLLM, and I'll explain why. And first, we should say why, or how does vLLM fit inside RL? Even though it's a form of training, you can see here that inference is a pretty important part with the blue line, where vLLM is used in all the places. When you're training an agentic model and ultimately testing the model on various environments or games or things that you want the model to see how well the model predicts and works on them, you need to run a lot of inference, or rollouts we call, from your current model weights in an inference framework like vLLM. And so we're constantly doing this for every forward and backwards pass through the trainer, getting dozens, if not hundreds, of samples from the current weights we have, judging how well the model does on that, figuring out how we need to update the weights, and then updating the weights in vLLM itself, and then doing that loop all over again. And so vLLM has been a key part of being the inference framework of choice to implement in many of the reinforcement learning libraries in the community. Hopefully you recognize some of them. You know, we're really thankful for the amount of co-development we get to have with this with the users of RL and these frameworks, and scaling up to the very large scale that people are you know, scaling RL up to nowadays. And so, you know, we're working on things like you know, stabilizing and making wide expert parallelism you know, useful for RL. As people are fine-tuning, you know, models like DeepSeek at scale, introducing batch invariance so we can have better on-policy RL, or sort of reduce mismatches from the inference and training processes that are, you know, running with maybe vLLM on inference and Megatron on training. Other, you know, nice APIs like pausing and resuming inference as we're doing, you know, weight synchronizations and needing to clear the KV cache. You know, allowing for memory-efficient co-located RL, where we can share GPUs between the inference process and the training process with vLLM sleep, and router replay, which is really important again for on-policy RL for large MOEs. Yeah, so we'll leave it there. And then, of course, once the models are trained, they need to use, you know, tools and you know, modern APIs that the, you know, coding agents and various agentic applications are building on top of. So we support, you know, the responses API in vLLM in tandem with, you know, OpenAI's help on the GPT-OSS launch. And we also, you know, have worked to support the Anthropic Messages API, so you can use vLLM to host, you know, a Quen model and run it directly with Claude Code locally. Which we can definitely see a lot of usage now with the OpenClaw and Claude bots that people are making. So to recap, you know, vLLM's purpose is to give timely, accurate, optimized model support for whatever hardware you're running on. You know, abstracting over the hardware so that the operations you want to run, either on your models or on your infrastructure, can be fast, regardless of the hardware. And we're working on all these different sections right now, where you know, we'd love to have your help or your feedback on if we should change the priority or change the focus. If you want to get involved, as I mentioned, you know, all of these special, or all of these subparts I covered are special interest groups, or SIGs, in the vLLM Slack. And you're welcome to join the channels and ask questions there. And of course, we have, you know, weekly meetings for all of these. In various different time zones. So you can ask things face to face with us, or at least over Zoom. Yeah, we hope to see you as a part of the community. So thanks a lot. And I'll pass it on to Dan Alistair. Dan Alistair.
All right. So yeah, thanks a lot, Michael, and thanks to Sasha and everyone else who put this event together. So my name is Dan Alistair. I'm a professor at ISTA near Vienna, and I'm also I've been working with Red Hat AI for since the acquisition of Neural Magic. I'm local, so I'm very excited to see the vLLM meetup happening here. So today I'll talk a bit about our research and how it's making, our research on quantization and how it's making its way into vLLM and trying to give people actual speedups. So the basic idea behind quantization is that we want to improve the efficiency of AI models via compression. So the basic observation is that most modern AI models are basically sequences of large matrix multiplies. This is kind of the standard equation that you get if you look into attention. And then the second, the trick here is that if we were to perform these multiplications over a compressed representation, so if we reduce the bit width at which the matrices are stored when they get fed to the tensor core, let's say, then you get an improvement in both energy and computational speed. So basically you can get a 2x if you do your matmul in 8-bit and then 4x if you do 4-bit, and so on and so forth. And if magically we were able to do everything in 1 bit, we would get massive speedups. Unfortunately, this is not yet possible, but we're working on it. So the good thing is that basically compression is orthogonal to many of the performance optimizations that Michael described. So we can kind of apply it together with distributed deployment and so on. However, if you've worked with quantized models, there's always this question of what do we lose by reducing the numerical precision. So kind of our job is to bring you the speed without the accuracy cost. So the way the quantization basically works is essentially like in this transformation where you have the original weight distribution, those are real weights on my left, and then you essentially bring them down to a set of, let's say, linear quantization levels, essentially to build a histogram, and that's kind of your simplified representation over there. And this you can do in 2 ways. One, which is kind of the standard way, which is what's called post-training quantization, which is what vLLM LLM compressor does. So essentially you have an already trained matrix which has kind of lots of colors, it has lots of information, some of it is noise, and then we're essentially going to sort of replace it via methods such as GPTQ with a sparse, or with a quantized, or sometimes even sparse representation that's intuitively much easier to store, and therefore it's going to be easier to compute with. Another set of techniques that I'm not going to talk about, but we're also researching, is basically quantization aware training, where you can train or fine-tune the model sort of in lower precision directly. So that's something that I can discuss afterwards, but I'm not going to talk about. So if you look at the way compression research is kind of being funneled today into products such as vLLM, you can quantize or distill or prune various components of massive models, and if on Hugging Face, for instance, you can find compressed versions of pretty much all of the open weights models, and then it really depends, like it really depends what the hardware support you're aiming for. So, for instance, on GPUs you have FP8, you sometimes have int8, int4, FP4. So essentially, you can have various formats, and these can be supported using various families of kernels. Okay. And then the nice thing for me as a compression researcher, I've been working on this for more than 5 years, is that recently there's really been a lot of community excitement about this. So essentially, back in the day, I was lucky if 20 people sort of read my paper, but now there's, like I was just checking recently on Hugging Face, there have been more than 55 million of sort of models produced, downloads of models produced using our GPTQ format. This was actually last year. I'm sure the number of models, the number of downloads has increased. So one takeaway from today's meetup is, interestingly enough, this is actually made in Austria. This is technology that's made in Austria, and it has had some non-trivial impact in the world. Okay, so I want to maybe move towards the more researchy part of things. So tell you a couple of things about the things that we've been working on, and some of the things we're going to be working on and deploying in vLLM in the near future. So the key question I want to start from is that of what is there such a thing? Like, will we ever get kind of lossless quantization? And this question was inspired by the following tweet. This is someone online who was very, very upset about the fact that they ran a quantized model in production, and apparently some of the benchmark results were not what they thought they were. So basically, the thesis was like, give me BX15, give me the original model, or give me death. I'm never going to use like a quantized model again. And then, like, when I see stuff like this, I get really, really upset. And what I do when I get really upset is I call our quantization whisperer, who is Eldar Kurtic, represented here. So he's kind of the Chuck Norris of quantization. His basically his motto is 0.001% accuracy loss. So we try to understand. Like, first we really try to understand, what is this person talking about? Is there really consistent accuracy loss? So then what we ended up doing was kind of a state-of-the-art study of what the impact, what the real-world impact of quantization on accuracy is, and this made it into a paper that was one of the top papers at ACL last year. So basically, we ran a lot of methods. So basically, pretty much all the popular methods that are supported in vLLM. we specifically the ones that have mature hardware support, so you would actually care about running them. So for instance, 4-bit weights, 16-bit activations, so basically int4, which was very popular at the time. And then we also looked at weight and activation quantization in 8-bit, because this is what the support was when we started the study. And then we did a very large range of benchmarks, so essentially academic benchmarks, such as the OpenLLM leaderboard, but also a bunch of generative, long context reasoning benchmarks that were kind of coming up back then with the emergence of reasoning models. And then we looked at a lot of models. If you look at the study, we had a lot of standard ones, but also some of the more recent ones like DeepSeek and Distills and so on and so forth. So all in all, more than 1 million individual model evaluations. You're welcome to have a look at the study. I will not run you through hundreds of thousands of evaluations, but I'll just try to give you the gist of what we found. So the first finding is that FP8 quantization is pretty much lossless. So basically, at least the models we released via Red Hat AI on Hugging Face, they're pretty much lossless. It's very, very hard to identify any loss on average, kind of on average recovery, and whenever there is a difference, it's usually benchmark noise. Then, when tuned properly, basically all of the compression approaches, even the ones where the weights are mapped to 4 bits, but the activations are kept in 16 bits, are within 1% of baselines on pretty much all of the easy benchmarks, so basically standard 0 shots. But you can drop more, let's say 2 to 3% if you are looking at harder evaluations. Okay, but one thing that we really found via this study is that there's a lot of noise in the evaluations as well. So often you're pretty much within the random variance of the eval itself. Okay, and then the second finding that seems to be very clear is that if you're deploying large models, then you shouldn't worry that much about quantization because they do seem to be strictly easier to compress. So you see more, but the downside is that you do tend to see more drop if your model is large, if your model is small. Okay, so we validated this across many different models and data sets and so on. So I'll invite you to have a look at the paper or ask me questions afterwards. So very reasonable questions like where do we go next? So basically, our next frontier has been to actually look at quantizing both weights and activations to 4 bits, which has the advantage that it can give you a 2 to even 4x speed up on the matmul itself, which is what I was describing at the beginning of my talk. The problem here is that it's known that activations in large language models are extremely hard to quantize because they have this kind of weird jagged structure. There are essentially channels which can have very high, very high values, whereas their kind of surrounding channels have very small values. So if you're trying to quantize these together, the high ones will essentially obliterate any information that you have in the small channels. Okay, so then there are all of these techniques that are trying to circumvent this issue. And one mathematical way, I promise this is probably the only equation I'll show you, is one mathematical way to get around this is basically by the following trick. So essentially, let's assume we have a linear layer with weights x, or with weights w that's acting on activations x. So basically, your matmul is going to be w times x transpose. Then what we do is like we replace this. We essentially place this invertible matrix R here onto the weights and onto the activations. Notice that if I didn't have any function Q for quantization, then the matrix R would just disappear because it's going to be multiplied against its inverse. However, the point is like once we apply quantization, there is some kind of non-trivial thing happening there because the kind of the rotation doesn't necessarily, the rotation R doesn't necessarily go out or fold out of the quantization. So the point of the rotation is essentially to smoothen out your, let's say, your activation distribution from something like this, which is very hard to quantize, onto something like this. Okay, so you're essentially applying this rotation in order to smoothen your input, and then basically making it easier to quantize. Okay, and then if you get the basic intuition behind this, the advantage is that you're going to be able to understand many of the sort of state-of-the-art methods in the area, because they pretty much what everyone does is trying to come up with different ideas for what this matrix R is going to be. So people come up with diagonal matrices, tuples matrices, whatever. There's all manners of techniques here. So unfortunately, what we noticed is that if you actually try to deploy these techniques in production, you still are going to break, and in particular, you're going to make LDAR very unhappy because the accuracy recovery is quite bad. So you're essentially going to drop more than 10% if you look at the harder evals, which is definitely not something you want to do because then you might as well just run a smaller model. Okay, so then we looked around what the options are, and when we noticed that recently, pretty much as of last year, both AMD and NVIDIA, they essentially introduced new formats, these kind of micro-scaled FP4 formats that should, in theory, be better for representing both weights and activations in 4 bits. So I'll try to explain this to you and just very briefly. So remember, we had this kind of integer uniform grid on top. And then what these formats are doing as their first step is that we say, okay, they say we want a floating point like grid, so therefore it's going to be tighter towards 0 and sparser but more spaced out towards the larger values. So this is intuitively going to be better for weight distributions that tend to have outliers. Okay, so that's the first idea. We just change the grid. We don't want uniform grids. We want them to be more spread out. The second idea is that they essentially allow you to change the quantization granularity from tensor-wise, so basically you're quantizing, I don't know, 1,000 or 10,000 values basically together, to very small groups. So essentially the NVIDIA proposal has 16 weights that are quantized to FP4 together, but they share a single scale factor. And then the AMD's proposal, so to say, it has 32, but still the groups are very small. The problem when you start to do this is that so essentially you have these 16 values that are packed together, but the problem is you're going to have a lot of scaling factors because every 16 values create one scaling factor. So what the hardware engineers had to do is essentially they had to come up with a way of quantizing the scaling factors themselves. So you can see how this kind of becomes more and more complicated, but the point of it is that they proposed a kind of nice way of sort of implementing this kind of low group size quantization, and this is naturally supported by the hardware. So you can, if you pack your data in the right format, then you're going to be able to multiply it very quickly. And then what does quickly mean? Well, you can actually get speed on current Blackwell GPUs. You're able to get speed ups between 2x and 6x relative, or I think on some GPUs even 8x. Relative to the FP8 baseline. So there's a clear win in terms of performance. Okay, so the promise from the hardware promise is that this is going to work great, and it's going to pretty much put quantization researchers out of business, or at least we have to find some new problems to work on. So we actually tried this just to see what happens, and we were very surprised to see that it doesn't work exactly as advertised. So I'm not going to show you the whole table, but the point I want to make here is that first, these kind of FP4 the FP4 format is actually not significantly better than the Int4 format that we had before, and the AMD MXFP4 format is really terrible. So basically, it's much worse than what we used to have in Int4, which was supported back in the day on Ampere. So we were kind of surprised to see that this is happening. So we actually spent a bit of time poring over these results. So first, we established that no format is lossless, and this is not just an artifact of these results. This happens. Other people have also noticed this. NVFP4 is marginally better than Int4, but certainly not lossless. And then techniques based on rotations that I actually described before, they actually fail. They really don't work in the context of these formats, which is specifically with respect to NVFP4, which we found really shocking because we've been developing these techniques. We were very, very surprised to see what happens. But still, classical techniques such as smooth quant and GPTQ, they still continue to help, but only by minor margins. Okay, so these are the findings in short. And now, then we kind of were dazed and confused, and fortunately, one member of my team who's here, I invite you to shake his hand afterwards. He actually we started looking together on why this happens, and there's a very nice mathematical explanation for why it happens. So basically, the distributions of weights and activations, they're essentially long-tail distributions. So these are the distributions in red on this slide. And once you apply rotations, then they essentially become these smooth Gaussian-like distributions. And then if you actually work out the math, you can prove that rotations actually are actively bad. They kind of, on average, they're actually going to worsen your quantization error relative to NVFP4, and they actually would help MXFP4 a bit, but the format is so bad that it doesn't quite make that much of a difference. So, I mean, there's a lemma you can prove about this. Maybe we skip the lemma, because I promised I wouldn't run through more equations. And the point is, you can actually validate this on various like real weight, sort of real weights, real activations, and so on. It's very clear that the theory is valid. So we essentially notice that the small group sizes, this kind of long tail distribution actually will have lower error, so which is an advantage for the NVFP4 format, but for larger group sizes, basically the normal distribution would have lower error, which is why transforms used to help for previous formats. So the real question is, can we do better? And we actually were able to get a better approach, which is nearly lossless in many cases. So essentially, we came up with a special transform, a special rotation that actually has very small group size, that actually sort of smoothens the weight and activation distribution, but not too much, in order to actually preserve some of the properties that make it fit well onto these FP4 formats. And then we're applying a specialized version of the GPTQ algorithm, which kind of shifts errors around. So essentially, we apply micro rotations, which smoothen the activation distribution, but not too much. And then we perform some kind of error compensation step that's kind of specialized to these FP4 formats. And the really important thing that really kind of unlocked the whole thing was the fact that we were able to implement this fast on GPUs. So the fact that these rotations are very small, they're usually 16 by 16 up to 128 by 128, it means that they can actually be applied efficiently onto the activations and runtime, which does essentially doesn't add you too much overhead. Okay, so essentially, these are some results on aggregate over multiple runs that Vahey ran, and essentially what you can see is that our method is significantly better than anything else on MXFP, so basically the AMD adopted format, and it also gives you up to 98% recovery for weight and activation quantization if you're using NVFP. Okay, so that's a very brief description of the research. This will appear in iClear, I think, in 4 weeks. This is up to very recently, this was the state-of-the-art accuracy preservation for NVFP and MXFP. Okay, and here the second thing I want to sort of highlight is the really excellent work that Roberto Castro, who's now with Red Hat AI, did in order to support this efficiently in vLLM. So basically, we're able for decode. Basically, for the decoder prefill phase, we're able to get speedups of more than 2x for large batch sizes using the micro rotation code that he wrote. And maybe the other thing that I want to highlight is that the code is open source. If people want to look at it or extend it, this is a library that we released a couple of months ago. Okay. So, the key observation here is that we can be fast. We can support these kind of rotation operations pretty fast. And then the interesting thing is that one challenge that we're looking at right now is that the fact that this worse format with 32 group size is actually much faster on NVIDIA GPUs. So we're trying to leverage this in order to get a method that actually does preserve a lot of the accuracy, but it also gives you the additional speed up. So I'll just end on a slight forward-looking note. So one question that we've been working on together with my student Jiale Chen is whether we can further improve the transforms beyond the micro-rotation Hadamars that we were using in the paper I just presented. And he essentially found the optimal solution. So essentially, you see, like these are the original activations. You see the transformed activations using our previous work. So you see still some jaggedness, and the scale is, even though the scale is reduced. And then you see his optimal transform is essentially extremely flat. The data becomes extremely flat, and the scale of the dynamic range is extremely small. So this is also going to be integrated in the process of being integrated in vLLM. And then one other thing that we're working on with other people from the room, I invite you to find them, is essentially trying to get extremely massive amounts of compression for very large models. So in particular, these are results that we have obtained very recently. This is the Kimi K2 thinking model that has 1 trillion parameters. So we were able to compress it to 2 bits per parameter at a loss of accuracy on GSM of less than 1 point on average. And we were able to get it to ternary for a loss of accuracy of about 2 to 3 points. So we're working on kernel support for this and to actually get more models out and so on. So this is kind of future work. So I want to end maybe on a couple of points. So we're really racing towards the limit in terms of what can be done with weights. I've shown you some ongoing work for weight and activation quantization, where I think there's still potential for some improvement. And then there's still a lot of questions of like how low can we go? Like can we actually get close to this kind of 1-bit barrier for quantization? Okay, and then one last thing for those of you who are students, we have research internships available in the lab. So in case anyone's interested, please get in touch. Thank you. And now for the man himself.
So, yeah, thanks a lot, Dan. So yeah, my name is Aldar. I work as a principal research scientist at Red Hat and also IST Austria under Professor Dan. And basically the main kind of topic of the research is inference acceleration. Dan just explained how we are doing this with quantization. Now I'm going to show you how we are doing this with speculative decoding. Speculative decoding is like a relatively new technique, which is completely orthogonal to quantization, so we can combine them together and get compounded benefits from both. The topic for the talk today is going to be like a tutorial style, so I'm not going to go into any like specific algorithms that Michael mentioned in the beginning, like dflash, parallel eagle, and so on. Mostly because I want to keep it like approachable for everyone. So after this, you should be able kind of to get hands-on experience with any of the algorithms that Michael mentioned before. So contrary to all of the compression techniques that you heard of so far, like quantization, pruning, knowledge isolation, and so on, speculative decoding is a lossless inference acceleration technique. So whenever we're doing quantization, pruning, knowledge isolation, we always have to run a lot of evaluations to like convince ourselves that the model that we have compressed is still doing the same thing as the original model, so that we are not destroying the accuracy. Whereas with speculative decoding, we have like a guarantees that the output that we generate with the speculative decoding is going to be the same as the output that we get from running the original model. However, this does come with a trade-off compared to all of these other techniques. Getting a proper, like a speculative decoding model is much more computationally heavy process than any of the other techniques. So it's like a trade-off. Like we have to pay the price somewhere. The main idea of speculative decoding is to make use of a draft or a speculator model to propose tokens. And then these proposed tokens are verified by our larger or target model in a single pass. And then this gives us the ability to boost performance, as I mentioned, without sacrificing accuracy. And this is done in a way that every accepted token is guaranteed to come from the same distribution as if it was generated by the target model. So if we take our original model that we want to deploy, we generate a bunch of text with that model, we plug in speculative decoding there, we can generate exactly the same text. And we have like mathematical guarantees that are going to like ensure that this is going to happen. Given that, of course, our speculative decoding model has been trained properly. So now I'm just going to show you, like maybe guide you step by step through the process of how this works during inference time. So basically, when we start with speculative decoding, instead of having just one model, we have two models. The target, the green one here, is a target model. So this is our original model that we want to accelerate. The second model that we're going to load as well on our GPUs is the draft model. This is extremely small, but also like very, very fast model. kind of just to give you like some number for comparison, it's usually order of magnitude smaller than the target model that we have, sometimes even more. And that's going to be the crucial piece of the story in order to get the benefits during the inference runtime. So once we load these models, like the first stage of the process is going to be, is my microphone working? Okay, I can just speak up it. So in the first phase, we have the first phase is called like a draft generation phase. So basically what we're doing here, instead of taking our prompt through the original model, we pass our prompt through the draft model. And then we run this autoregressively as any other LLM. So we just generate one token at a time. The main thing that we have to pick here, like the main hyperparameter that we have to choose is the number of tokens that we want to speculate. In this specific case, here I'm like picking 4 tokens that I want to speculate. So we just run one token at a time with the draft model. We produce all of the tokens. Then we come to the phase 2, which is called like a parallel verification. We take all of the tokens that the draft model produced, and inside the single forward pass, we go through the target model. And as like the LLM inference works, at the output of the target model, we're going to get some kind of probability distribution. So now that we already ran like a forward pass through the draft model, forward pass through the target model, we have probability distributions generated by both of these models. And now, like, we have to decide whether we're going to accept or reject some of these tokens based on the exact probabilities that these models produced. So what's going to happen here is like we go to the third stage of this process, which is called rejection sampling. So we basically compare these two probabilities, and there is like some math which tells us that if we do it in this specific way, we are guaranteed to like recover the original distribution of the model. And this is where this like a lossless factor comes in. And the way it works is like relatively simple. We just take the probabilities, we compute the ratio of the probabilities that the target model produced over the probability that the draft model produced. And then we just clamp this to the range 0 to 1. So it can be interpreted as a probability. And in this specific case, for the first token, let's say here, like the token over, the draft model was 70% sure that this should be the next token. The target model said it's 65%, so the ratio is 93. So with probability of 93%, we're going to accept this first token as a token that we would originally produce. For the next one, like we have 40%, 38, the ratio is 95. So with the probability of 95%, we're going to accept the second token as well. However, for the third token, we see that the draft model assigned the probability of 30%, the target model assigned the probability of 5%, and the ratio of the two is like 17%, which means that it's very unlikely that we're going to accept this token during inference runtime, and it's most likely it's going to be rejected. And then based on this ratio, we go over the tokens, and then we sample like one random number from 0 to 1, and then we compare it with the probability of accepting the specific token. Based on that, we accept or reject. So for the third token, most likely we're going to reject this one because it had very low, let's say, agreement between the draft and the target model. So what we're going to have to do at this point, once we find a token which we have to reject all of the following tokens, right? Because the draft model, when it generated all of the following tokens, it generated them based on the assumption that all of the previous tokens were correct. So this is the part which we'll come back to later on when we should not always like overshoot when we're picking the number of tokens that we want to speculate. We shouldn't say like speculate 50 tokens at a time, because it's very unlikely that all these 50 tokens are going to be accepted. So we might be just wasting a lot of compute, knowing that the model is just going to reject them at some point, and then everything afterwards drops. So there is one more nice feature that we are able to leverage here when we are doing this parallel verification step, is that we are discarding the third token here, but then as standard like LLM inference, for every token in the sequence, we're always going to get the full probability distribution of what the next token should be. And then we can just go back to the last token that we accepted and say, okay, given this token here, we get the probability distribution of what the next token should be. And then this gives us ability to generate one more token, like plus one token literally for free, because during this like a parallel verification step, we already computed all of the probabilities. And therefore, we kind of resample this plus one token just because we already have all of the probabilities. And then it's going to be probably like a lazy. for this sentence here. And this wraps up the inference pipeline of the a standard a speculative decoding scheme. And as a result of this, we got 3 new tokens generated. If we are now to compare the pipeline of the standard autoregressive text generation, in order to produce the 3 tokens here, we would have to run 3 forward passes through our large model, right? We take the prompt, do 1 forward pass, produce 1 token, pull back this token, do again forward pass, pull back the second token, do again forward pass, and roughly the time is the time needed to produce all of these tokens is more or less the same. So the total runtime to produce 3 tokens without speculative decoding, we can say on average is 3 times the forward pass through the model, like depicted here, denoted by the TT time, so time for the target model. If we look at the speculative decoding pipeline, we see that in order to produce those 3 tokens, what we had to do and kind of the cost that we had to pay was basically 4 forward passes through the draft model. So because we speculated 4 tokens, and then we had to do only 1 forward pass through our target model, where we in parallel verified all of these K tokens. So the total runtime for the speculative decoding piece was 4 times forward pass through the small model plus 1 forward pass through the large model. As I mentioned before, whenever we are designing the speculator model, we choose this model we kind of try to get it to be as small as possible. Usually order of magnitude, even more smaller than the original model, which means that the runtime to go through the speculative decoding model is usually much smaller than the runtime through the larger model. If we kind of assume here that this is negligible time compared to the target model, we see that on average the cost of this is 1 forward pass through the target model. So this is not going to be in practice, as you'll see later on in the real world. It's just approximation, just to give us a feeling for what's the speed up that we can get out of this. So for 3 tokens, it's 3 forward passes in the normal regime, 1 forward pass plus some residual in the speculative decoding setup. And now one thing that I also kind of approximated here that some of you may have noticed is the fact that I'm using the same box size, so the same runtime for 1 forward pass through the original model, to produce 1 token, and 1 forward pass where I have K tokens. And I'm using the same runtime for both of these. And this is the second part that. Yeah, so this is the second part that the speculative decoding is based upon, and that's the fact that usually in these cases when our inputs are not large enough to keep the GPUs busy during doing matrix multiplications, forward pass with 1 token and with K tokens where K is relatively small usually costs the same amount of time. And this is basically, I'm just gonna on the next slide show you. If we now take, just kind of to illustrate what this means in practice, is that if we now take a model, for example, Llama 3.370B model, and then we record decoding time to process 1 token at a time, 2, 4, 8, 16, and up to 64, and then we measure the slowdown relative to 1 token at a time, we're going to get something that looks like this. If we are processing 1 token, 2 tokens, 4 tokens at a time, the runtime is going to be exactly the same. And this is because whenever we have very small inputs for our setup, here LLM inference is usually bounded by the memory bandwidth, not by the compute. So the main cost that we are paying during inference is to load the weights from HBM to SRAM to tensor cores, and then the actual computation that happens inside tensor cores is literally for free. It doesn't matter whether it's computation with a matrix which has just 1 row or 2 rows or 4 rows. It's going to be exactly the same amount of time. However, as we start increasing this, so we go to 8 or 16, we start seeing some slowdowns, like 5%, 8%. And then if we increase this to 30 to 64, then we start seeing something that we can measure in the real world, like slowdown of 20, 50%, and so on. And this is the second part that speculative decoding is heavily based upon, because this here enables us to hide the cost of this parallel verification step. If you recall, the previous slide, this the standard autoregressive pipeline had 3 forward passes through the large model just to get 1 token, whereas with the speculative decoding, we packed all these like k tokens in a single forward pass, and then we said this is the same amount of time as generating 1 token at a time. And this is kind of the second part that speculative decoding heavily relies upon, and that's the reason why we can get speedups out of this setup. So now we're going to see like this was like just a general like a story here on what speculative decoding is about. But now we're going to see just some like a real world measurements on what you could expect to see in practice if you're about to deploy speculative decoding for some specific use case. So here I did the benchmark where I took Llama 3.370B model. I'm sending prompts which are like kind of math reasoning prompts, basically from the GSM-8K dataset, and I'm comparing the latency given a different number of the requests that are coming to the server. And as you can see here in the specific setup for the speculator model that I'm using, we can get speedups like anywhere from 1.3 up to 2.7x. And this 2.7x is literally this part that I approximated before, where I said 3 forward passes through the original model, 1 forward pass in the speculative decoding, but this like 3-to-1 ratio is just kind of roughly approximated, and this is where this 2.7 comes from, because there is always some additional cost, like to run the drafter model. It's not 0; it's like some small amount of time. There's one important also like part to like clarify about speculative decoding, and that's the fact that this is not a golden bullet. Like, it will not always give you like 2x, 3x speedups in your pipelines. There are some use cases where speculative decoding can harm your So there are some cases where speculative decoding can actually be harmful for your deployment. And this kind of comes back to this like regime when we bump up the number of tokens, and then we get at some point, like when we have 32 or 64, we get to this regime where we are starting to noticing the slowdowns. And then in this specific use case here, we are looking at Quant332B model, and it's like doing some coding tasks. So we are sending some coding prompts. What we can see here is that like in the first part of the graph, whenever we have a smaller amount of requests that we are sending to the server, we are always getting some kind of speed up from the speculative decoding. However, at some point, once we hit like some kind of threshold where the inference like switches from the memory bandwidth bounded to the compute bounded regime, we start seeing slowdowns. And this is because now we have a ton of like requests coming to the server, or just the model is generating a lot of text, and therefore it's not able kind of to process the inputs that we are sending in this kind of negligible amount of time that I said before when doing math models in the tensor cores. And at this point, like speculative decoding becomes a problem, because now it's just like additional overhead that we have to pay for to run the verification, to do the speculation, and so on. But in the real world, it's not going to bring any gains. In fact, it's just going to slow down our inference. And this is like the other kind of important part of the real-world deployments and the tools that we built around vLLM, is that these things are things that you can simulate with the tools that we already have, and kind of based on your like workloads, on your desired GPU, setup, model size, and prompts, you can see in which out of these two regimes your inference is, and whether you're actually benefiting or you're gonna just pay the price for nothing for using speculative decoding. So yeah, it's not a golden bullet. There are cases where it helps, but there are also some cases that you have to be careful with. And now, if I'm able to change the slide, if you would like to start with speculative decoding, so if this was enough kind of to motivate you to try it out, there are like two ways to do this. The first one is like you go to Hugging Face Hub, you find some speculative decoding models that community produced, and you plug them inside your vLLM. However, one of the main problems that we found so far with the like a random community produced models is the fact that they're usually not as of good high quality as you would like to have in the enterprise environment. Therefore, like Red Hat AI team is like maintaining a Hugging Face hub where we are actively releasing speculator models, where our team already did like a heavy due diligence to confirm that the models have like a proper accuracy, that they have like proper speedups in all of these like benchmarks that we care about. So if you go to our Hugging Face hub, you will see speculator models for many different models like Llama, Quen, GPT-OSS, Quen MOEs, and so on, and we are actively updating this like on a monthly basis. If you open up any of these model cards, you're going to find the first thing that you will find there, you'll find like a details on how this speculator model was trained. So which data sets have been used, how it was trained, and so on. Usually for all of the models that we publicly release, they're like a general models trained on like a general data set. So they should have a decent performance across coding, math reasoning, summarization, like all these categories. And then the first kind of thing that you want to look for is like what is the average acceptance length that you're going to get if you are about to deploy this model. And here we like usually go over coding, math reasoning, text summarization use cases, and we measure the average acceptance length given a different number of the tokens that we speculate. So K here is the number of tokens that we want to speculate. So we usually go from 1 to 7 just to get a rough feeling for what's the amount of tokens on average that our model is going to accept if it was about to use this speculator. And then if you scroll down below that part, we also provide like a real world measurements from a vLLM server. So if you're about to deploy, so the first part was accuracy, the second part is actually the speed up that you're going to see in the actual deployment. And then we all like run the same setup across different rates that we are sending to a server, and then we just measure the speedups and then the plot the graphs. The main thing here is that like because this is like a real world, it's like these curves are not always as smooth as they are. So what we do, we send first one request at a time, then we send the most number of the largest amount of requests that the model that the server can handle before it's like saturated, and then we interpolate between these two extremes. We repeat multiple times, and then we fit a line through this to give you like a graph which tells you like on average what you should expect if you're about to use this speculator model in this specific use case. And then, yeah, in the end, it's very simple to use this. So you just use the standard vLLM serve command, and you just like add one additional argument, which is like -- speculative config. You point it to the target speculator that you want to use, and the only hyperparameter you have to set is the number of tokens that you want to speculate. And that's basically it. vLLM is going to take care of everything else. The last slide that I have for today is just like, as I mentioned, all the speculator models that we release are already trained for like a general like setups like coding, text summarization, blah blah blah. If this is not something that is like relevant for your own deployment, for example, you have some use case where you want the model where you're deploying model just to be like a chatbot, or you're deploying to do like code completion in some specific like programming language. Usually you would benefit more if you train the speculator from scratch on your target dataset. And for this purpose, kind of we have inside vLLM project, we have a library called speculators, where you can like have this entire pipeline from scratch, from the data generation, collection of the hidden states, and all these like necessary steps to make the speculator model like train properly, and then the final like a training code. So you can do end-to-end process on your own internal data set, which will always give you better performance than having like a generic one that we probably trained on like a standard like open source data sets. And there, like I just took like quickly like a screenshot from the speculators repository, where you have already a lot of examples for popular models like GPT-OSS, Llama, Quen, and so on. So you can just plug in your data set there and rerun the full pipeline and get like a model which is tailored for your specific use case here. And with this slide, yeah, I'm gonna hand it over to Sasha.
Does anybody's brain hurt yet? A little bit? No? I guess it's a very smart city. So we're going to change the schedule just one more time for the second time today. I think we should take a 10, maybe 15-minute break quickly, get some water, get some drinks, stretch our legs, and then we'll come back for 2 more sessions, one from NVIDIA, one from Canva. Should run around 40 minutes. We'll try not to go over, and then we'll do a fun Q&A. Ziv has some fun questions planted already, but we're also looking forward to your questions. So let's do a quick 10 or so minute break, and we'll be back.
Hello, everybody. Hello. I hope you enjoyed your break. Now it's time for the second part. I hope you don't fall asleep. So, my name is Dan, and I work in the AI DevTech team at NVIDIA. We mostly focus on CUDA optimizations. And today I'll be discussing communication in MOEs, and basically why we end up with these communication patterns, what parallelism we use, and why. So what this presentation is for, this presentation is for me a couple of months ago. So I knew what an MOE is, I knew what tensor parallel and expert parallel and data parallel, all of these like basic things, but I didn't know specifically why we would prefer one over the other and kind of what communication patterns we use for each and why. And I hope you'll learn this by the end of this. And just a hint of how to put this in practice. I won't cover in depth anything realistically in this presentation, and there will be plenty to nitpick if you want to nitpick, but yeah, it's just an overview. So let's start with a quick refresher on what a mixture of expert looks like. So just a basic LLM, right? You have some number of transformer blocks, right? And each transformer blocks is attention, where you have a bunch of requests. You need to correlate them with each other, so you need to correlate the tokens within each request to each other. And in the feed forward part, you do not have this concept of request. You just kind of flatten all tokens, you just pass them to some matmos. This is the basic idea. Now, let's look at one token. So one basic idea of deep learning is instead of just doing one operation, do more operation and do some like weighted sum between all of these and let the weights be defined by just back propagation. And this is kind of the idea. And these weights kind of imply an importance. So what if in the interest of efficiency, you don't load the least important parts? And this saves HBM for inference, so this saves memory bandwidth. And I've basically described what an MOE is. In this case, I show one with one shared expert and two routed experts out of 4. And when we plug all of the tokens back in, it looks something like this, right? You see this kind of random-ish pattern evolving here. Now, what if this model is too large for a single GPU? Or let's say you could fit it on a single GPU, but what if it's too slow for users to realistically use? Now, we have to split it on multiple GPUs. How should we do that? Well, one idea is this kind of classic idea of tensor parallelism, and I won't spend too much time into it if you don't know it, but just a very quick rehash. So it's this idea that if you have two matrix multiplies after each other, what you can do is you can split the first matrix column-wise, so first part of the column stay on one GPU, second part of the column stay on the other GPU, and the second matrix row-wise, so kind of similar idea. And when you do on a replicated input, so you replicate the input and you pass it through these split matrix multiplies, at the end you get 2 parts of the result, 2 parts that if you sum together, you get the full result. And if you have 2 parts of the same matrix on 2 GPUs and you want to have a copy of the sum on both GPUs at the end, this is kind of the definition of a null reduce. So we've just kind of stumbled into the definition of a null reduce. And this is why tensor parallelism needs a null reduce, right? And attention uses a very similar mechanism. It's a bit more complicated. Let's not dwell on that. Just know that it uses an null reduce if you're using tensor parallelism. And this is kind of how a graph looks for a dense model. This used to be state of the art a year ago or so. So just one slight abuse of notation from my side here. Tensor parallelism in attention mostly, so we use it mostly for splitting of the KV cache and the KV heads. And on the dense part, we're mostly using it for splitting the weights. Yeah. Now, how do we apply this to the full mixture of experts image? So we can try and start with the kind of basic idea, right? So the basic idea is we have two separate workloads. So we have a KV cache heavy attention, and then we have a weight heavy MOE part. So we want to kind of see if we can solve that. And we have two competing goals. So generally, GPUs are more efficient when you have big matrix multiplies. And generally, users are happy when they get fast responses. Now, the familiar attention tensor parallelism, what it gets you is it kind of fixes, right? It helps with the KV cache. It doesn't help with the MOE. And now you're kind of in this middle part, right? And what we can do for the MOE, again, just stretching out the TP, is you can just apply TP for it as well. But now you're in an area where you have, for each GPU and the MOE, you have 5 experts that you need to run through, and they're smaller now. So you've really pushed it to a point where you're not utilizing the kind of most efficient method possible. You're having relatively small matrix multiplies. Now, what you can do instead is this idea of, instead of doing, so now you're splitting your matrix, your experts per GPU. So now GPU 0 will hold a shared expert. And I know this is a kind of a dumb, naive distribution. We'll get to it in a second. The second GPU holds the other experts. Now your matrix multiplies are larger because you're not splitting them on 2 GPUs, and you're doing less of them. So the amount of work that you have to do is essentially the same. You're just utilizing it more, the power of the GPU more efficiently. And this is, at the moment, a pretty standard deployment for low latency, or like throughput at latency idea, right? That you want good throughput while you meet some SLA, some service level agreement, some token per second per user. Now, what if you want actually to parallelize this further? One issue that you run into is that if the number of KV heads is less than the number of GPUs, you will not be able to split. Just in the way that tensor parallelism works on attention, you will start needing to replicate your KV cache, which is less than ideal. So especially in high throughput cases, you really don't want to do that. And the way that you can kind of get around it is by this idea of attention data parallel. Sorry, the boxes are a bit screwed up because of presentation copying. The idea here is to just put separate requests on separate GPUs. You duplicate a bit of the attention parameters, but it's relatively low cost when you have big enough requests or plenty of requests that the cost of this attention parameter duplication becomes quite low. Now, what you need to communicate now? Well, token 0 and token 1 will need to go to actually GPU 1. So you need to kind of cross these two GPUs together, right? So just send the tokens over to the other. But what if we add more GPUs to this picture? It becomes a bit more complicated, right? In this 3 GPU picture, again, just looking at what tokens we need to send to what GPU. So from the perspective of GPU 0 and it's doing the MOE, it wants all tokens. From the perspective of GPU 1, it wants all tokens. And for the sake of simplicity, let's just do the same on GPU 2. And this is what you get, right? This kind of every GPU reads all tokens, which is the definition of an all-gather. So we've kind of, again, stumbled into the definition of one of these collectives. And then, right, this is between attention and the MOE, but how do you get the requests back? Well, let's look at one example of a token. So token 4 in this case. For token 4, you need to sum it up across GPU 0 and GPU 1, and you need to send it back to GPU 2, right? So reduce across multiple GPUs and send to one specific GPU. And this is, kind of by definition, a reduced scatter. So this is, if you're familiar with vLLM and kind of these these communications, this is the all gather, reduce, scatter pattern. Now, one issue is wasted communication, right? The last GPU will get from its peers will get token 0, token 3, and well, token 4 is debatable since it was already there, but still, it's wasted communication. And this problem is actually much graver than what I'm showing here. In DeepSeek, and this is what some colleagues of mine measured, on DeepSeek you see that there's very drastic differences in the number of tokens you route per expert. So this is basically the number of tokens that each expert will get for a specific MOE layer. I hope this is clear. So you see, for example, if you're using expert parallelism as I just showed it, in this red spot over there, if you're doing a naive all-gather, that GPU over there, which barely needs any tokens, will actually need to receive all of the tokens. And this problem persists across experiments, across layers. This is not like a one-off cherry-picked example. And the way you fix this in practice in a kind of a proper way is called expert parallel load balancing. Michael kind of hinted at it earlier, but I won't go into today. Just know that it's a problem and it needs to change the way we communicate. And the way we communicate needs to be kind of a bit more informed. So in this case, yeah. So you need to send token 1 to GPU 1 and GPU 2, right? This is the dumb thing, right? It's pretty basic. But what do you need to do with token 3 in this case? You want to send it to GPU 0, but you don't want to send it to GPU 2. So you want the router to actually give you the information. You want to communicate based on the router's information from all GPUs to all GPUs. This is the definition of an all-to-all. This is the idea of an all-to-all. And at the back, right, so again, router feeds information into the all-to-all. You do this nice thing. How do we communicate at the end? Well, unfortunately, it's not exactly showable on this slide, but just trust me that the reason why we need an all-to-all at the end as well is because of these sparse communications. We don't want some collective that forces us to do a reduction across all tokens. So this is, again, an all-to-all, basically. And if you've ever heard of these terms, now you also understand what dispatch and combine are. Dispatch is the first all-to-all between attention and the MOE, and combine is the one at the end when you're reducing or combining all tokens back into the thing that you feed into attention. And this is kind of the standard deployment for max throughput, right now, at least. Now, you've seen the all gather, reduce, scatter backend from vLLM. It literally is named that, all gather, reduce, scatter. And then kind of the all-to-all, the proper all-to-all, is implemented in Deep EP. It's called. It's kernels from DeepSeek and with help from NVIDIA. And then the Flash Infer multi-node NVLink. We won't go into that today. It exists, but for us specifically, it's more interesting right now to look at why does Deep EP have two kernel families? So one kernel family favors high throughput, many tokens, which is good for pre-fill workloads, and one is good for low latency, so purely decode. And why would you do that, these two extremes? Because this is not amazing if you have a mixed batch, which you would from what I presented today. Well, this idea of disaggregated serving comes in and helps us here. Disaggregated serving, in very broad strokes, just basically means that instead of having a server that does both pre-fill, right, you're getting a new request, you have a lot of tokens to process, and decode, you've processed all of the requests, it's in the KV cache already, you just need to load the HBM, through HBM you need to load the weights, and you need to load the KV cache, just do one token like this for a kind of regular batch. It just does this all of the time. And this is what disaggregated serving does. Now, where's the catch with this image? Because there is a catch. The catch is, as you see in this image, that you might want to have different setups for prefill and decode. And the problem becomes now that the config space, you're trying to decide what is the best configuration for prefill nodes. You're trying to decide what is the best configuration for decode nodes. You're trying to do a Cartesian product out of all of this, how many instances of a prefill and a decode you want, and so on. It just gets, it's a combinatorial explosion. And you have some constraints, right? You want some time to first token, you want to respect some time per output token. Now, how do you choose between all of these? Well, first, it's important to realize that you cannot benchmark that. Like, it is not reasonable to actually throw that and benchmark through all of these. And this is what AI Configurator, it's a tool from the Dynamo team. So Dynamo is the thing that NVIDIA provides. It's the software that NVIDIA provides to be able to do disaggregated serving at scale, at a data center level. And they also have this kind of very nice side tool inside of it, which basically you specify the model, you specify how many GPUs you want to deploy this on, you specify some data set statistics, right? You kind of know what your users want. Maybe it's a coding task, so that's actually like 80,000 tokens or something. Maybe it's just simple chat, so it's a bit less. The SLAs, right? How many tokens you want per second, and AI Configurator will actually give you all of, like, actually, let me show you in this image. So again, you specify all of these, right, which I mentioned previously. It's a simple CLI, and you get a full Pareto front. So you will actually get the disaggregated serving compared to aggregated serving across the whole front. And you will see here all of the deployment scenarios which offer you the best throughput in total for the SLAs you've specified. And it also generates some configs that you can actually then deploy with Dynamo. So to close all of this up, so you can have rules of thumb across all of these, right? You can, TP helps latency generally, attention DP helps throughput, EP is good if you, it's better than MOE TP at least. But when you're doing disaggregated serving, it's far too complicated to go through all of these, right? I hope this quick tutorial helps you in at least understanding why some of these things are the way they are. But generally, just check it into AI Configurator, and if you see some horrible results, raise a GitHub issue, and it will get solved. Yeah, that's it. There are some other parallelisms that we could get into, right? I have some backup slide here. They're very interesting, but I don't have the time. And I think the ones that I just mentioned are kind of occupying the most headspace right now from what I've observed. Yeah, thank you. And we are hiring if you know CUDA.
Hello, I'm doing a talk on wins and challenges in hosting LLMs. My name is Georg Narodoslavsky, and I'm actually an MLE in Canva's AI platform, and I'm doing mostly like performance tuning for inference and also for training. So I'm not sure if all of you know Canva. So Canva is like an online design tool. So you can use it to make like nice looking documents, sheets, presentations, social graphics, but even do video editing or order print products like mugs, stuff like that. And what many probably don't know, there's also a size. So we have over 265 million active users. So they create over 400 designs per second. And we're actually over 5,000 employees. And some of them also sit in Vienna. So I'm part of that. So we have a hub in Vienna. And this was actually the home of the background remover feature. I'm not sure if you have ever used Canva. It's like a very popular feature. You have a random image of your pet or, I don't know, a product, and it just removes the background pixels from it so you can nicely use it in a design. And nowadays we develop AI to enhance productivity and creativity, and we're actually 80 employees across Austria. And today I'm going to talk about like our adoption of vLLM, why we did it, what were some kind of challenges, like real-world production things, and then talk about different wins that we had using vLLM, like different tricks that we also saw before, like in our real-world experience deploying it. So why did we even want vLLM, right? So we had like LLM inference with like transformers library, do a classic forward, but this was somehow not enough for us. We wanted more performance. So in around 2024, we were looking in all these new inference engines, and vLLM had already quite outstanding performance. So the specific graphs here are not really important. And it also had already good adoption. So it was picked up with like on GitHub user stars, but also in the industry. And what's also important is like a stable production company. It was easy to integrate. So it supported multiple Python versions. It was not too strict on what packages it wanted. It had regular releases. Yeah, all that's important to us. And we had broad model support because our machine learning engineers, they want to do products with the latest models, so we need the latest models. And actually around this time, it became like the standard that vLLM had first day support for new open source models. And how did we integrate it in? So we saw before like this vLLM serve command, but that's not how we could easily integrate it because we have like an existing stack. So we have an existing RPC layer that has like many modern features like feature flags, canary rollouts, telemetry, tracing, all that. And we sit in a big monorepo. We have like we have one set of dependencies across all our services, and we do container-based deploys. And there were a few challenges. And the first one is like not being able to use vLLM serve. Was like vLLM serve spins up an HTTP API server that is OpenAI API compatible. But we have our own thing. But there is like a nice solution for that in vLLM. It's the async engine. So this is the thing that actually powers the OpenAI API compatible server. And you can spin like on top, you can spin up this like async LLM engine and give it the same parameters that you would pass on CLI. So all the things that we have seen today also work there. And then you can use this async engine to add requests to it. So there's this predict function, there are other functions, and basically they will add to the vLLM scheduler your new request. It will go to a model runner, and basically you have like an async generator. It streams back the tokens that vLLM produced on. We send this then basically back through our RPC layer. So our model forward call was just replaced by this, and internally it's a lot more complex, but also a lot more powerful. Another challenge for us was like the first L in LLMs, that they're really large, but in a slightly different fashion than you might think, because we were looking at 70B models, and they are like 130 gigabytes in FP16 precision. And as I said, we do like container-based deploys. And what we normally do is like we have an image with all our model code and also the model weights baked in the single image. This is super nice because we can ship off this image. If we want to do a rollback to a previous version, we change the image. So quite easy, but it was like a problem if like your weights are now 130 gigabytes. And for instance, in our container registry that we're using, the limit for a single layer is actually 50 gigabytes. So we could not even get these weights. I mean, we could split them up in layers, but it's all a bit annoying. And also we have like a very nice build system. Bazel works great for large scale enterprises, but it's not really meant to ship around these gigantic artifacts. So if you put them in an image is basically just layers of tar files. It has to copy them around. It has to cache them, all very annoying. And so it's resulted in an hour build. And our solution to that was actually quite simple. We separate the weights from the image. First easiest idea, we put them up on S3 or any other object storage. At runtime, when the server starts, we download them, we read them from disk. But that's actually a bit slow because like downloading that in like, at least with standard Python, Boto 3 client is not very optimized. yeah, we need the disk. The disk is also not super fast. Yeah. But vLLM has like two nice solutions for that. So the first one that we explored is called Tensorizer. This is a project by CoreWeave. And basically you stream straight from S3 in chunks in parallel. But you first need to convert your model checkpoint into the Tensorizer format. So they have their custom format that you can understand. So that was a bit annoying already, the conversion step, because we had to do this like post-training or for off-the-shelf models. And also there's no FP8 support as vLLM understands it. So the thing that LLM compressor outputs, Tensorizer does not really handle. There is another solution that's called Run AI Model Streamer. And it also streams from S3, but it supports now safe tensors. So that's a lot easier to integrate this. I think all models are released in safe tensors nowadays. Yeah, and we did some tests and we actually used that. So basically what we see is if we use the standard naive S3 download, we are around 8 minutes in time. And for Tensorizer, we are already down to 40 seconds. But with the model streamer, we get down to 10 seconds, which means that all of these GPUs together read like 13 gigabytes per second, which is like really a crazy number. And you see like how much read speed you can get out of S3, and that's like impossible to do with any disk, really. And you might now wonder, why does this even matter, right? Because you say like, I start my model server once, I wait 8 minutes, I wait 10 seconds, I really don't care. But we actually scale up and down all day, right, as traffic shifts. And this means we can scale up a lot faster, right? We don't have to wait like 8 more minutes. I mean, we have to wait a bit for the GPUs to provision and all other things. And if we scale up quicker, that means we need to have less spare capacity, right? We want to stay in a certain latency budget. And if it takes very long, then we get overloaded. So we need to have more spare capacity to not get overloaded. And if we scale faster, we need less spare capacity and fewer over-provisioned GPUs. So that was already a win that was provided by vLLM. But now I also have like more like standard performance tuning wins that I'm gonna cover now. I do like a quick recap. Not sure if everybody is like aware. I think we have heard the terms many times here, but want to go over it once again. So if you have like a standard sequence that you would send like to a server, you have like I had here in this simple sample, the system prompt in violet, the input tokens in blue, and then all the output generated tokens in orange. So we have like this prefill phase where we populate the KV cache with our input token values, we compute the K and V values, and then we decode one at a time. And that's an important distinction often for like what optimization helps where. So we try to categorize problems if they're prefill heavy or decode heavy. That makes our performance life a lot easier. And automatic prefix caching is a very simple technique in vLLM. And what it does, we reuse previous computed prefill values. So if you have like a large system prompt in like one-shot or few-shot learning prompts, where for multiple examples, then the prompt is often quite big, then you don't have to recompute the prefill KV cache values. Or if you do like multi-turn conversations, like in chat or something, then you can go to the same server and reuse those prefill tokens. And that's actually on by default in vLLM. And it will decrease the time to the first token. So the first output token here. So if you don't have like a big prefill, this doesn't really help you. Important to keep in mind. But what I like about it is that it just works, because there are sometimes other solutions or providers where you have to do like explicit cache write instructions so that you make use of this prefix cache, or there's certain token size limits. So basically only if you have 1024 tokens in your prefill, it will be cached and everything else will not be cached. And there's actually still a gain also for smaller requests. So in a workload that we used, this is like very prefill heavy, so only a few decode tokens and I think around 700 prefill tokens. This basically got us like a 6x on the time to the first token and still a 3x on the time to the last token. So this is your total request time. Then Another thing that we quite like is, and we also have heard already before, is like FP8 inference. So I think it's very important to understand. I think also Dan said this before, but I want to reiterate on that. When you say your model is in FP8, only your matmos are in FP8. All your scalar operations, like doing a ReLU or dropout, they will still be in FP16. So how it actually works is, from one layer, your activations come in FP16, they will be scaled down to FP8. And they will be scaled so that they fit this FP8 range, as we have also seen it talk before. And then you do the matmul with your pre-quantized FP8 weights. And actually in the matmul, the output is already stored back in FP16, so the accumulator is already in FP16, but still you need to scale it back to the original range that you had. So you do the inverse of the scaling that you did in the blue box, in the dark blue one. Yeah, and right, in theory, we see all this like, we should use only half the memory, have twice the bandwidth available, twice the compute, and no accuracy loss. So how does it look in practice for us? So how we normally do it, we use the LLM compressor project. That's also part of vLLM. And there are different recipes in there. Our go-to recipe is like called FP8 dynamic. What it does, it will scale your weights into the FP8 format. So, but your activations will be scaled at runtime. So that's what the dynamic means. What happens here in vLLM itself, you get the activations in, and then we'll look at the distribution of the activations and figure out what is the scale that's needed to fit the FP16 values into the FP8 supported range. So you don't have to calibrate and figure this out before for your workload. So you can basically send any workload through it. And this is actually part of our standard suite now, because we have tested this in various use cases, and we always do like a quality check. We do the FP16, then really look at the FP8 one, and never saw any quality reduction. And the real end-to-end speed up that we often see is around 1.5x on GPUs that support it. So on NVIDIA, that's Hopper and newer, or also Ada Lovelace. But it actually also works quite similarly on older Ampere GPUs, because there's also these like specialized Marvin kernels in vLLM that support this very well. Yeah, and memory usage is really halved, so that's nice. And why this matters, there are like a few things actually. I showed this like big weights are annoying to load. Those weights are also only half the size, so it's a tiny win. And yes, you can have like more KV cache, to fit more sequences in parallel or bigger contexts. But what I also like is we can basically use larger models on smaller GPUs, right? So we don't have to, for like big models, we often have to use tensor parallelism, but this only works very well if you have NVLink, so that it only works in high-end GPUs. And that way you can go like one tier below. You can use like L40S or RTX 6000 or some these GPUs, because you fit on a single GPU, and tensor parallelism doesn't really work so well on those GPUs that don't have fast interconnects like NVLink. Yeah, and another technique we're using that we heard today is like speculative decoding, but we use actually, I think, one of the simplest options there that are in vLLM. It's called engram speculative decoding. And the reason for that is like it's a model-free approach. So you don't need to train a specific model for that. And this is often nice because it's very easy to enable. It's just basically a flag. And if like your model is changing, you don't need to retrain something, which is also often happens to us, or the practitioners want to switch out the model for a new generation that looks totally different. And how engram speculative decoding works, basically, if we already have like an existing token sequence, like here, this preheat the oven to bake at 350, then place in the oven. So now we would look for the next tokens that we want to speculate. And engram looks back at like single tokens or pairs or triplets, so that's the N, and sees like what has already appeared, and then guesses that the same tokens might appear afterwards. So this is very helpful if you do like few-shot prompting where you have like a given structure and it's already in the prompt, then you can refer back to that and it's most likely the same thing. Also, if you have like very repeated output structures like JSON or HTML or something like that. Yeah, so here it would look basically back, say I have already seen the oven thing, I speculate to bake out, and then I do the same thing that Elder has told before. You send it to the big model, do the acceptance sampling. Yeah, so that's the same bit. One thing that I recently learned in the docs, basically it says it only looks at n-grams in the prompt. But what it actually does, it looks at n-grams in all the contexts before. So if you have also output tokens already generated and they're repeating structures in there, it will also pick that up. Yeah. And I would really advise that you tune like how many tokens you speculate on. But there's also like this prompt lookup max that basically says, do I look only at like single tokens, pairs, triplets, all that? Because what we have seen, so we often do then a grid search of all these combinations with a benchmarking script, and we see like 10% difference in performance. So overall, similar point to Elder, speculative decoding is really nice for latency sensitive setups. And often our use cases are latency sensitive because we are online and our engineers are quite happy if we don't need like 3 seconds, but 2 seconds to get back to the user, because this makes the user more happy and more engaged in a session. And what we in general see is like around a 2x speed up or reduction, however you want to see it, in the time between the tokens. So it won't help you with time to first token if your prefill is really big, but you're very decode heavy. This can help. And for n-gram, you need this property that you somehow need to repeat yourself or reference back to the prompt. Like summarization would also be a use case. And the last optimization is actually, I think, probably was already in the first version of vLLM. The main idea is basically doing multiple requests at once, right? So not going once through the model, but batching those together, especially as we have heard, the decode steps, they are memory bound. You can do more compute here. And we basically just did like here a concurrency of 1 to 5. So we always keep the model busy because we pull from a queue and always have like 1 request or 5 requests in vLLM itself. And basically, if we go to 5 requests, we have like 3.5x the throughput, but we also have like a penalty on the user latency that we see, right? But if we have like a certain budget that the user is okay with, we can basically trade this off here. And so I would really also advise that. And it's also really easy to do with the async engine because you just add more requests to it. Yeah, that concludes my talk. I think we don't have time for questions here, but you can also hit me up on the floor later. Yeah, thanks for your attention.
Hi. Oh, hi. Works. Let's do a Q&A. What do you guys think? Maybe 10, 15 minutes? So if we can invite all the speakers back, I think, George, you can totally stay if you want. Yep. I'm sure there'll be some questions. Nice job, by the way, George and Dan. Now, I did see George was running a timer here to see how long he has. So I told my team they have to take this as an example, and they will. Anyway, so I'm going to pass it over to Ziv Ilan from NVIDIA. He'll run this Q&A. He'll start us going with a few questions. I already gave Ziv some vLLM socks for doing this, so I'm going to give you vLLM socks as well if you ask a question. So here you go, Ziv.
Thank you, thank you, thank you. You want to sit or stand in awkwardly?
Better to
awkward it is.
Okay. So I have 2 questions, and then in the meantime, guys, think about what you want to ask. I'll start with Michael here. I think about 50% of the room haven't started to touch vLLM yet. What would you recommend as a starting point for them?
Should I get the mic? No. Yeah. You should start using vLLM. You should, pip install it or Docker pull it and, use your local GPU at home. You can run vLLM on Windows subsystem for Linux. I do that on my gaming desktop at home.
but also like renting or using even a Colab GPU, just running it as a server or even through some of the offline Python-based interfaces like was already talked about with the async LLM. There's also just a regular LLM class in Python, yeah, just start building things on top of it. Now especially with all the agents and tool calling, I think it's a really convenient way to plug in the latest model. I play around a lot with like the smallest Quen models of the day because they're really, really fast, especially when you put them on B200s. So, running like a Quen 3.5, like 8B, can be really, really fast. And you can start seeing for yourself, yeah, if I plug this into Claude Code, like can it do something or get a more tactile feel for the models yourselves. Yeah.
Thank you very much. And maybe a question for George, Georg. Yeah, well, you showed a lot of nice features. Like, how do you discover this, right? Like, it's not like you have a playbook, you need to do this and that. Like, what was the process for you at least?
Yeah, it's very different. I follow all kind of material. Like I really like the office hours. So they happen every other week, and they're like the latest releases summarized. I also go. I also go through release notes and click on PRs that sound interesting because especially I think the PRs often then really have like throughput numbers or something like that. Why this feature was important. Yeah, I think that's the main resources. Also, the blog has nice articles. Yeah, so that's what I do.
Cool. Thank you very much. Any questions from the audience in the meantime? If there are people in other rooms, they can come here probably and ask questions. We don't have any streaming. You had a question?
Yeah. Hi, I'm Dean. My question is maybe a bit off topic, but I'm more interested in security and privacy. So what would be like, I still haven't started using it. If I start, what would be the maybe 3 key things that I should keep on watch and be careful for? Thank you.
Like, do you mean like security vulnerabilities in vLLM itself?
Yes, and then connect inside as well, but what if we feed it with sensitive data as well? Like
Yeah,
for exposing and maybe intercommunication inside what's happening.
Yeah, so there are actually like a few features to deal with like, well, obviously you have like an API key that you can put on the server and it'll only accept requests, but there's also things like cache salting. So, or other things that sort of like separate the KV cache between users or users that like access and want to like hit the prefix cache only for their sessions because there's like some information you can leak between sessions if like, yeah, you're sharing prefix cache, at least as a security researcher concerned. Yeah, I mean, honestly, I would recommend going through many of the security advisories and updates we've had in the project. We actually take this very seriously. We have like a vulnerability management page in the documentation, and we go through, like the official like GitHub like reporting and like responding and I forget the term process, but so I've been involved in a few security vulnerabilities myself. There's a lot of researchers that are interested in vLLM for that, and we like resolving them. We really appreciate things that are found. Yeah, there's a lot of like crazy things that people have found. I think like some of the most common ones are with multimodal data. And often like specific things with like specific models, like, oh, maybe one model has like a weird pre-processing trick that it does. And so if you like change the alpha transparency of your PNG between 2 things, you can like leak information, like crazy stuff between requests. Most of it is also kind of, because it's a server, ultimately, like, can a user like deny the service? Can they cause some, memory overflow or some storage overflow, log overflow? There definitely are things that can there's a lot of like holes to find. Some of them are like reasonable and some of them are not for like such a widely used project. Many people that serve VLM at scale, they're going to wrap it and put restrictions in their proxy in front of VLM. And it doesn't make sense for VLM to restrict it by default. And we also have like a dev mode environment variable that allows for more unsafe things when you're doing like RL at scale and you need to access the, inner process weights and things of VLM. So we can kind of go both angles.
Or deploy at the top of the Red Hat platform and let us worry about this. Like NTS says, relax, you relax, we'll care. Cool, thank you.
Yes, over there. Okay. And if you have a specific person you want to ask, also mention it. Otherwise, I'll
just ask,
yeah.
and
okay.
whoever feels like answering, it's fine. So I recently found out that you can use Ollama in order to serve some LLMs locally for cloud code. And now when Michael mentioned about cloud code, I was thinking that maybe you can, so is it possible to use vLLM to serve models for cloud code, for example, instead of Ollama? I would be mainly interested in whether you could use speculative decoding for the agents.
I guess I'll answer. Yeah. I mean, definitely speculative decoding is maybe most useful for agents and low latency as you really want to push that interactivity. Yeah, and I mean, like, as I mentioned before, like you can use VLM with Cloud Code, with Open Code, with many of the coding assistant libraries. Yeah, I mean, like Ollama and like llama.cbp are still like really good options for running like on your local GPU. Ultimately, like VLM isn't meant for batch size 1 inference, which often it can be if you're the only one talking to it. Now it gets a bit more interesting when you have like these agent harnesses that maybe you're the only one talking to it, but maybe it spawns off like a swarm of agents, and so it's really doing like batch size 8 or batch size 16, and they're sharing a lot of context, and so you'll get prefix cache hits. And VLM can be really efficient at batching that. There's a lot of interesting stuff that people are doing there. But VLM also does other things that maybe aren't so friendly to running on your personal laptop. Like in the pursuit of performance, it will allocate all the GPU memory it has available because it's more efficient than allocating it dynamically. Whereas so people get confused about why is my model taking up 80 gigabytes when it's only 8 gigabytes. Whereas like if you're using Ollama, like it only takes up the minimum memory required for a single request. Also because it only really runs at batch size 1. Like it's less meant for batch inference and serving multiple concurrent users at once. So VLM is kind of more of the production and data center GPU scale. Ollama and llama.cbp, they're really good for the sort of local and lightweight use. So yeah, it's kind of just whatever you value more.
So for the compressor, how much does the calibration dataset matter? Like is it specific, or if it's big enough, it's just fine, or?
Yes. So yeah, I have. So in general, in the ideal case, what you want to do for a calibration dataset is to pick the samples from the dataset from the distribution that you care about. So if you're quantizing a model for coding, you ideally want to get like a coding data set to calibrate on, because the main point of the calibration process is to like trigger the activations in the model and see how they behave given your data set. And therefore you'll be able like to predict how to quantize them properly. In general, like if you're doing like a general model, you don't care about any specific use case, then you can just use any like instruction tuning data set. For example, we very often use like Open Platypus as like a really good default if you just don't have any specific domain in mind.
Maybe how much is the difference if you use a specific one? Is it?
So it's usually a couple of points in the in terms of the accuracy. So your model is not gonna diverge completely if you use like a wrong data set or something. It's more like on the scale of 1, 2, 3 points on the accuracy side. So yeah, it's kind of just like squeezing the last bits of the performance that you can get out of the model. Oh yeah, the number of samples, yeah, that's a really good point. Usually what we do is like 500 to 1,000 calibration samples. And that has been like a pretty stable default, like for most of the use cases we have seen so far. You can also go more above that, but at some point it's like 2K, 4K is gonna start saturating the accuracy, so you won't be getting any further gains out of it. And also like maybe one good note for everyone here is that like, if you go to the Hugging Face hub of Red Hat AI, we have a lot of quantized models out there, FP8, Int8, Int4, FP4, all these schemes. And for every single model, if you open the model card, you will see exact script used to quantize the model with LLM compressors. So you're going to see what was the number of calibration samples, which data set was used, which dampening, blah, 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 all these hyperparameters. So you can basically like copy, paste, plug in your model, and rerun the quantization script to get the like high quality model to start with.
Disclaimer is that I've never used vLLM because my field is on diffusions and autoaggressive video generation. Does vLLM support like autoaggressive video diffusion, for example? Because I've seen many ideas like speculative decoding could be applied for diffusion models, right?
Yeah, so there's no diffusion sort of architectures landed in vLLM yet. Most of the work on like diffusion transformers and diffusion models is currently ongoing in vLLM Omni. And there it's, obviously for the Omni models, but also for like, just diffusion models like QuantImage or like the Flux models that like pair an autoaggressive backbone and some like diffusion transformer output. We aren't really working on like DLLMs at the moment, as there's not like a really compelling model out there yet that's that people tell us they really want to use. There's like really interesting results like Lalada recently starting to make some good model checkpoints. We're like starting to experiment with it. But yeah, from like the core maintainer perspective, we only have so much bandwidth, and but we have some like community efforts that are spinning up around that, and we do think some of that could land in the main part of vLLM, especially for autoregressive text models. For speculative decoding, there's dflash, which I mentioned, and we already have some like draft PRs posted for integrating that, and I do expect that to land. So using diffusion, just for speculation. But it still will be a interesting thing to see how that'll be used, and you're sort of stuck using bidirectional attention instead of causal attention, and the attention kernels we have available are not as heavily tuned, especially on like Blackwell architectures as what we have for causal. So yeah, it's kind of an ecosystem problem as well, and it's more than just us supporting it. We need to also see a lot of usage in order to, get the ecosystem effect ultimately. Yeah, but it's definitely an interesting space. Yeah.
So when there is a vLLM installations that you are using for different tenants, what mechanism are in place in vLLM to prevent each other to, I don't know, abuse a resource or protect from each other? You mentioned that it's possible to avoid having a common key value store. Are there other mechanisms?
Yeah, I mean, I guess like from the are you talking from the perspective of like a performance concern or like a data leakage concern, I guess? Yeah.
But, so the main concern is always, of course, the data leakage, and then the second concern is like if you have the noisy neighbor problem.
Multi-tenancy?
Yeah, in multi-tenancy.
Yeah. So I mean that the noisy neighbor problem is more
something you need to manage from your service level, right?
Mm-hmm.
Like you can control like how many requests you're letting vLLM run in parallel. And very often there's like a sort of concurrency parameter that people will set. Also at the vLLM level, you can set like maximum sequences. And this limits the maximum batch size of decodes or maximum batch tokens. These are all things you're setting up as you're meeting your latency SLO for your service. Yeah, like of course you can have like maybe some requests that get sent for like a really large context, but like yeah, there's not much vLLM can do itself. It's going to run what requests you tell it to run from your service planning level place. You need to take care of routing or rejecting requests that are too busy or making them wait. Yeah, and from the security perspective, a lot of the security concerns with like sharing prefix cache between requests and whatnot are like not really founded, I guess. Like the amount of data leakage you can get is very minimal. It's more that you can realize, someone has a shared prefix on the server. Like someone else has sent a request like this in the past because the latency is faster, or because my log probs are like slightly different. My numerical properties are a bit different. But and the ways to work around that is you as a service operator disabling prefix caching or like setting up cache salting. Yeah, there's plenty of options to like remove the performance in order to add some guarantees, but that's yeah, it is unfortunately like a pretty a manual thing that you need to figure out and develop yourself, because people care more about performance generally.
Okay, thank you.
Hello, I also have a compression question to Georg, because you mentioned the LLM compression functionality from vLLM, and that it halved the memory usage of the model and also sped it up by like
1.5.
1.5? Okay. What was the impact on the performance of the accuracy of the model in that case? And I got a follow-up question in that case, because I never did LLM compression. Is there a way to fine-tune the compression so that the trade-off between memory usage and accuracy is not that high? And also like with a grid search approach or something.
Yeah, so we didn't see any on like accuracy. So however you evaluate really then the model's output end to end, we didn't see any impact. So it was always in the, as I also mentioned in Elder's talk, in the variance of the evaluation. Dan's talk, sorry. And there are, in these recipes, by default, certain parts of a model are excluded from quantization. So you would not quantize the LM head at the end, or the vision tower in like vision models is often excluded. But I think I would pass on to 10 because so that's the level to the extent that we did. But
yeah, I mean, I think we have an ongoing project actually on the second thing that you asked about. Basically, like, I mean, technically usually you get a Pareto curve saying, okay, like how much do you lose versus how much compression you get. So basically we're really trying to explore this using some new kernels that support like very fine-grained quantization. So you can do like 5-bit quantization or 7-bit quantization for some layers. So we have that ongoing, and then this also allows us to study like what exactly is the degree of loss. And for instance, in our experience, whatever you're seeing as variance in FP8, weights and activations, is just noise, it's mostly noise in the evals. We haven't really been able to find tasks where we can point to something saying, okay, like the FP8 model is definitely worse. I think Eldar is trying really hard right now, but it's actually, so yeah, I think the FP8 models you can just use them as is. I think there's lots of people who do that, and we're working on a way of doing like the whole Pareto curve. So you can basically say, okay, I have, 60 gigs on my GPU that I want to use for this process. Like, what's the best model I can fit inside these? Does that make sense?
Yeah, thank you.
Just one point to your question. FP8 as a thing, whenever people say it's quantized to FP8, that can mean at least 3 things in my mind. So there's like this FP8 per tensor, so you have 1 scaling factor per tensor, but then there's also other granularities of scaling factors that you can apply to your model. One thing that was really popular because of the standard of MX is this MX FP8, but there's also something that became super popular recently, which is this DeepSeek recipe, where you have some other granularity. So even if people will tell you FP8, actually look into what you're actually quantizing to, because these things will matter and can matter for performance, and there will be some middle ground for your use case. As Georg said, you can leave some layers unquantized. You can leave your KV cache unquantized. You can use a finer grained quantization scheme. You have methods that if you are unhappy with your quality, you can kind of scale back the degree even as is right now.
Maybe one also justification for FP8 is if you look at the very like a top state-of-the-art models released these days, most of them are coming already from model vendors in FP8 scheme, like Quen models, DeepSeek, Mistral as well. Like they already come in FP8 because we are already at the point where FP8 is pretty safe to use, so much that they are like able to stand behind the FP8 model and say it's or even train in FP8. Yes.
And also for diffusion models for the diffusion guy. A lot of them are already, even some in NVFP4. Last questions. Last question. Okay.
Hello, thank you for the talks. What is the business model that Red Hat has in mind for vLLM? I mean, like, seems like you are burning a lot of cash.
This question was not planted.
I'm not sure anyone here is.
It's the same as Linux, you know, enterprise support on open source software, and you do that best by being experts in the open source software. Yeah.
That should be a punchline on the Red Hat website. He hasn't been trained to say this sentence.
All right, thank you guys so much. Go this way. Felix, can you give me the slides back, please? I promise it's going to take 45 seconds. You can time me. All right, so I don't have to sell this to you, right? I think George, my new best friend from Canva, already sold you the office hours. So thank you for that. That's a great organic shout out. So we do, Michael and I run bi-weekly vLLM office hours. Sometimes they're weekly. I know it's an unfortunate time for you guys at 8 o'clock at night, but if you want to help us bring them here at a more appropriate time zone, we would totally collaborate with you. So if you're interested, let us know. They're all recorded. You can see some of the sessions, but we bring on NVIDIA and pretty much everybody here and more to dig into some awesome topics. So scan the QR code. If you missed the scan the QR code, you can just email me and I'll send you a link. And lastly, please, if you can just pull out your phones right now, we would really appreciate some feedback. It's only 3 questions. It should take less than a minute. One is a 1 through 5 scale, and then the other 2 are what's good and what's bad about this meetup. We really do look at the feedback all the time. We share it with the teams to make these meetups even better. So really appreciate your time. Thank you so much for coming. I think we have some more, maybe food, more drinks out there. We'll see you all out there. Let's continue the conversation.